All right. Hello, everyone. Thank you so much for having me. I want to talk a little bit about the work that we do and that I like to frame as at a physical AI. So, I already introduced me. I'm part of the Human-Computer Interaction Institute. I'm faculty there, and I direct the Interactive Structures Lab. So, most interfaces that we encounter are still somewhat static. So that means that they look for everyone the same all the time in daily life. Now, adaptive interfaces, so interfaces that adapt to your needs, as you switch context, as you switch task, things like that, that adjust to your context, are a very active area of research. And in fact, this image in the background is work of Professor Lindelbauer, also here at the HCII. And in this active research area, most of these interfaces that adapt are digital. So that means, the contents that are shown in the way that they're shown in their placement are being changed. But if you think about it, like we interact with, our physical world all day, every day. It has been physical for a very long time. We were always really good at building tools. And I would argue that it will stay physical as we move forward. Unless we're really in a simulation that we don't know yet, I really hope not. So I'm just going to operate under the assumption that we are in the physical world and it's going to stay physical. So in that sense, one of the things that have been talked about very recently is physical AI. So the idea that you have like physical agents rather than digital agents that can adapt to you and your needs. And the way that people typically think about physical AI is actually in this like generic large robots that are, can do multiple tasks and help you in many ways. Help you clean, help in healthcare, help in like many different areas. So if you would extrapolate this idea that you have like many butlers that all are there to try to help you, but you have then suddenly maybe all of these like physical agents around you. The question is this kind of like a way that, or the future that we envision? I think it's one future, but another future that we could also envision is like taking some of these capabilities and blending them into our background, into, the physical world that we are already used to. So the floor could adjust, maybe if you fall down, it turns itself into a damping property while otherwise being stiff as you walk on it. That little stool can adjust to as you change your pose. It could adjust to help you sit in an ergonomic way. The sofa, the walls and tables, things like that. Things that we are already familiar with, and that is what I like to call embedded physical AI. That they embed that functionality into the objects that we are used to. This relates to other research areas, so shape-changing interfaces, morphing materials, soft robotics, and things like that. So, robots are great because they're very strong, very generic, and do many things in one object, and are dedicated machines for those tasks. I think robotic materials can do things that are, that they will have less capability, will be more specialized and less generic. But they would have this nice factor that kind of like blend into the background, adapt to our physical needs as we change our context. So that leads to a few questions. So what are the needs we want to adjust to? How do we adjust to those? And also, when does the system know how to adjust? So what needs? One thing that is, that we are also familiar with are, for example, wearable interfaces. Smartwatches, for example, are always in contact with the skin, which is great because that allows us to communicate to users. It provides input, so eye news, so position and orientation sensing, bio signals, and many more. And then output, typically, today, right now, is often by vibration motors. And there's like some large force feedback being done in labs. Now, we're really focusing also a lot on the output part and wonder, well, what if we can use materials as end effectors rather than, kind of like an encapsulated unit to provide personalized haptic feedback? So what we looked at was at producing geometry-based output. So essentially, this is one project that we did where the idea was we have like many of these like 3D printed patches that can stroke over your skin and feel different. So you can print them in different shapes such that it encode the tactile, the way that they feel in the geometry. And then they're actuated by this body-worn common interface. So, for example, as a user may, have like be in this virtual experience, but a jungle exploration. They walk by some bush or leaves, get stroked by the leaves, and they feel that on their arm with the soft stroking tactors. Next, they explore this flower, but they did not expect that there's like some, spiders crawling out of them, and that activates the pinching tactors that actually pinch over the skin. And so the bigger idea here is really that as you design these virtual environments, most often you download these visual assets, which are 3D geometry, and use them in your scenario. So what we want to extend is essentially saying, well, these tactile assets are also just 3D geometry. So you could kind of like download both at the same time. You download the tactile experience with the visual, and then go ahead and print your tactile asset, plug it into your generic actuation interface, and have like the fuller experience in one go. This is an example of how these patches can look like. They are very, very versatile. So you can have different types of tactors so that they feel different. You can adapt the direction. You can change the density. So there's a lot of parameters that it can vary there. The only thing that's important is that there's like the common interface is just a linear pole, such that it can be integrated with this generic bracelet that then decides which one to actuate. So beyond VR experiences, you can also use these things, for example, on the back, because they have lots of area there for navigation notification for visually impaired users, for example, or other notifications as, who's calling you. Is it like, soft stroke for a friend, and maybe, I don't know, like for something more contentious, like a more scratchy stroke. They can also be very small and miniaturized because they're compliant and integrated, for example, also with smaller wearables like JASPs. So we can also go large and have like this more encompassing physical agents around us. And I want to show just this wall example here where the user comes home, has a bag in their hand, and as they enter the room, the wall folds out into a shelf at the right height. They just place it down at the same time. It creates a hook as they take off their coat and grab their bag again. The shelf folds back in, and the hook moves the coat out of the way. So those are some examples how these what type of needs we could adjust to in this way of like things blending into the background or into your wearables. Now the question is, how do we adapt to those? Because actuation is really hard, makes things bulky and things like that. So we have to be smart about that and also think about how to fabricate those and manufacture those and scale, for example. So in this wall example, the way that we went about, instead of having like big motors that have to kind of like, move long, lever arms as you fold out things, we opted for these tiny servos. They're the smallest, almost the smallest servos you can find, and they will rotate this clamp that just kind of like clamps these hinges to change the shape. That there's like some actuators on a wheel that push it together, and that actually has like a pretty large force output there. It can pull heavy things despite it being fairly lightweight and small. The other good thing about this type of approach is also that many of the parts can actually be fabricated by PCB manufacturing alone. So the black material is actually FR4, so the substrate that PCBs are made on. This is actually cut by PCB manufacturers. You could use, in this case, we used Mylar to kind of heat bond to fork those hinges, but you can actually have that ordered just in one piece by having like a flexible PCB in the center laid up with rigid PCB material on both sides. You can have the communication go through, the logic being embedded in those things. You do have to add, the servostat at the end of the day, but that's not that big of a task. The nice thing is that it's very scalable. So we can use these industrial manufacturing techniques to make these things a reality and really go for like the bigger vision there. So what we do essentially is that we combine passive geometry that does some small things with smaller actuations such that it makes it more feasible in a clever way that allows you to have like these applications that are encode tactile information, that can encode different type of furniture, dynamic furniture. So actuation is very challenging, so we're going small and combine that with passive geometry that then can be customized, is often compliant in our design, so that means that it scales down very nicely, but also up. It can conform to users' bodies and things like that, and can be manufactured in one process. So now, if we can provide all of this output, which is nice, right? The question is, how does the system know when to do that? That's a really big question, and I think that the time is really ripe now to tackle those questions in a profound manner. I want to show one more example of like how we're thinking about this. So here we used, again, this PCB manufacturing. In this case, it is a very thin, flexible layer. The actuators are so-called liquid crystal elastomers. There are also small, thin layers, and laying that up allows us to form a sleeve almost that it can put on the bottom of existing things to make them move around. So you can, retrofit any of your familiar objects and give them this movement capability. So in this case, we did that with this ruler over there. And the intention was to transform this ruler into a math tutor. So the user, the student is kind of like solving this problem, but then they get stuck. So the ruler can move onto that paper in the right spot to show them the next, where to draw the function, and to understand and, help them move forward in their learning. So how does it know, right, when to do that? A good tutor, should understand, should give people some time to think. But thinking of it from a system perspective, we could look for cues like, is the student gazing onto the paper, meaning that's their object of interest? Is their gaze kind of like maybe going up to the ceiling? It sometimes indicates that people are thinking about it. Is it fluctuating between those two? Of course, how long? Is there a pause in writing? Are they writing something then erasing something? Finger tapping and chin rubbing, things like that. Those more behavioral cues are things that we can look out for with appropriate environmental instrumentation, sensing, and find those to do user intent recognition. Similarly, on the wall, you can think about, well, the user has just entered their home, their hands are full, so they have their jacket on. Things like that can indicate that probably maybe they want to put down their grocery bag and take off their coat. So intent recognition is very, very challenging, but I think that the time might just be right, just because many things that used to be extremely hard just in a few recent years became much more easily solvable with AI and machine learning. This is just a work from Professor Chris Harrison. It's also in the institute, and so they are looking a lot on like gesture recognition, activity recognition, pose recognition. All these things were really, really hard. So I believe that this user intent recognition, we are getting to a way to understand really users more profoundly. So modeling user behavior is a big theme here. Of course, also modeling and designing the object's capabilities by respecting the form factor and also the tasks that they're designed for. So again, I think if we make less generic and more specialized things that allows us to create robotic things, robotic stuff that feels very familiar to us, but has enhanced adaptation capabilities to become what we need in that moment and also to fade into the background. And so the way that we tackle this, and I like to think of it as like a material robotic continuum, where on the one hand you have the very passive, standard materials that don't do anything smart, if you want to think of it that way, up to the other side of like big generic robots. Metamaterials come into play to alter material properties, for example. So the geometry of the material, you can design that to do something specific, still passive possibly. And there's many examples of that. The things that change their volume, things that change their damping ratio, for example, things that can also move as a block. And then we also design some things that have more like moving, like predefined like mechanisms embedded into the material itself. Here we also have the tactile information embedded into the material itself. We have shape-changing modular units that can together form like a bigger shape. The walls that again also have then more and more and more actuation in there. So you can really choose how much actuation do you want or need to embed to achieve a certain task, and move along this spectrum, as you choose and as the form factor gets appropriate. So I believe robots are great, but I also believe that our environment is great and the things that we are used to. And so this is the version that we're working on right now. And I want to acknowledge all of my fantastic lab and Jesse introduction. I'm open for any questions.